Okay, so let me start. Today I would like to calculate the dimension of the moduli space. One maybe of the top points of the course. Since we have compact Riemann surface gamma, I assume that gamma is smooth, compact, and has genus G. Now, first of all, you know that you have only one Riemann sphere. All complex structures on the Riemann sphere are equivalent. You know it or not? Here you had Riemann theorem in the complex analysis. Sorry. Okay, so you have it. But for tori it's not true. Why? Well, for example, you know that we have a torus, complex torus. For the complex torus, we have a holomorphic differential, omega. The space of holomorphic differentials is one-dimensional. Therefore, we have two basic cycles, A and B. A and B. And the space of one forms is one-dimensional. Therefore, we can normalize omega by assuming A omega equals to 1. Z equals to B, that's denoted by tau. Tau is a complex number, okay, I started. So, assume that we have a torus. Its surface of genus 1. Therefore, we have exactly one holomorphic differential on the surface. One-dimensional space of holomorphic differentials. Therefore, we can normalize by this condition, we obtain tau. Therefore, if we have a torus with a basis of cycles, we have exactly one complex parameters. We know that we prove that im tau is positive. Therefore, assume that we have a torus with a fixed basis of cycles. Then, two pairs gamma AB, and another pair So here we have a two pair of tori. One torus gamma with a fixed cycles A and B. Another torus with fixed base of cycles A prime, B prime. These pairs are equivalent if and only if tau is equal to tau prime. Now, because if tau is equal to tau, because what is torus? Torus is a factor of complex plane by the lattice, generated by numbers 1 and tau. Therefore, if tau is equal to tau prime, they are equivalent to the same torus as a factor of complex plane. Vice versa, it's invariant. Therefore, the space of such pairs, torus and basis of cycles, the space of such objects is equivalent to the upper half plane. Understand? And this is called Teichmüller space for the tori. The same is for any arbitrary genus. Assume that you have a Riemann surface with a fixed base of cycles. And we assume that the pairs are equivalent. If we have a map from one to another, which is holomorphic, and which maps the cycles A1, A, n to the cycles A1 prime, N, A prime, and B, and Z. It's therefore Teichmüller space for tori is the upper half plane. Sorry. So I'm repeating. Let me repeat. Okay. Therefore, now we discuss. We have the following object: a Riemann surface with a fixed base of cycles. Of course, if we talk about basis of cycles, it's in the homological sense. of course, we don't fix bases as curves. If two curves are homological, it's the same base, you understand? Of course, this basis is we can replace curves by the homological ones, and we have the same basis, you understand? So we have the following object, tori and the base of cycles. The space of such objects is holomorphic, is the upper half plane. Why? If we have first of all, if we have a torus, we have a one-dimensional space of holomorphic differentials. We can fix differential by assuming this. You see, the choice of A is essential. Then we have exactly one number tau, integral over B cycle. We have one-dimensional space, we use A cycle to normalize differential, and we proved in the previous lectures that imaginary part of tau is positive. Therefore, we associate with each torus with a fixed base of cycles a point from the upper half plane. Vice versa, if we have a point in the upper half plane, we consider the lattice generated by elements 1 and tau, because the torus is a factor of the complex plane by the lattice. Okay. This space is called Teichmüller space. But we can also consider the factor space, because now we consider not such objects, but simply curves. But we don't fix the basis. Therefore, if one torus one triple can be obtained from another by changing of basis, canonical base of cycles, they are the same points of the moduli space. Therefore, we have group of changes we can transform the basis of cycles. The group is SL to GZ. You understand? You know what that means, this group. It's a group of integer invertible matrices respecting the skew-symmetric form. Because on the cycles, we have skew-symmetric intersection form. Remember, introduced skew-symmetric intersection form. And we have a group of such a group. And if we factor Teichmüller space by this discrete group, we obtain the moduli space. Is it clear? Now, what happens in case of tori? In case of tori, the action of the group is the following. Tau goes to A tau plus B plus D. A, B, C, D are integers, and equals to 1. Have such a group. Okay, it's a good exercise that this group maps upper half plane to the upper half plane. I hope you can do it. And what now we can calculate fundamental domain. First of all, okay, let me leave as an exercise to you that. First of all, we have the one transformation. Tau goes tau plus 1. And tau goes to minus 1 divided by tau. Lemma. I will leave it as an exercise. These two transformations generate the full group, SL to Z. SP, but the cell is the same. It's a full group. Or a cell, you have the following transformations. I think it's simple exercise. Okay, do it. It's a good home exercise. Therefore, we have, and now, okay, let me provide you the answer. Consider the upper half plane. Consider such a stripe. First of all, you see that using the first group, we can always assume that we can put inside this domain by using the first. And the statement, okay, let me don't prove, let be an exercise for you, that the fundamental domain for the group is this one.
What do you mean by fundamental domain?
Because the fundamental domain means the following. First of all, any point can be moved inside this domain using this group. You can, by the way, you look internet, you can find easily the picture of images. The second statement is that if there are 2 points inside this domain, they could not be moved one to another if they are inside, using this group. Understand? Using this group. The only, of course, but of course you can move this point to this, you can move this point to this. No, you can also move this point to this, so, but okay. Moreover, moduli space is not smooth. They have made it's orbifold, not manifold. It's variety, but not moduli space. But the dimension of the moduli space is the same as the dimension of the Teichmüller space in generic points. Okay. So Teichmüller space is the upper half plane, and moduli space, you take this area, then you glue these pairs, and you glue these pairs. You understand? In fact, it will be sphere. Yes.
So again, we have this upper half plane.
Yes.
And
we apply this group. But this group is generated by these 2 groups. Maybe it's a good exercise to check that applying this transformation, we can move any point of the upper half plane inside this area, or to the boundary. But, and the point, if you moved inside this, it's unique point. If you are at the boundary, you have this or this. This is glued to this. So you obtain the effect sphere, you understand. After such gluing, you obtain the sphere. And this is moduli space. Okay, you understand? So moduli space is this. I draw this way. Moduli space, because you first of all you glue, you obtain cylinder if you glue this to this. Then this compactified to one point at infinity. and then you glue the upper half part to the center. Okay, it's moduli space. But the dimension is the same. Now, let me calculate. Now, let me prove maybe one of them. The top points of the dimension of the moduli space. How to modify the complex structure? You remember we started by the complex structure defined by a differential operator. Roughly speaking, if operator remember, and assume that it's non-degenerate, and it defines complex structure, remember. But of course, it's defined, we may use this dz plus b, any such operator. If you have such operator, it defines a complex structure, remember. When we proved the existence of isothermic coordinates, we introduced such operator and we constructed. Therefore, to define complex structure is the same as to write such an operator, Beltrami operator. Now, we consider deformations. We would like to calculate the dimension, like to calculate the tangent space. If you calculate the tangent space, of course, you assume that Z bar. Introduce such operators. We introduce small parameter epsilon, if you call small perturbations. But of course, if we introduce, but the problem is the following. Is the complex structure equivalent or not? If we can make an infinitesimal change of coordinates, killing this b, then it's equivalent. So the question, if such b can be removed by some infinitesimal change of coordinates or not. So, now let's study. So we have two questions at this moment. Let me remove it. So, first of all, what is B? The question, what is B? What is the transformation law of B? Let me check it. Because assume we make a holomorphic change of coordinates. Holomorphic. We have holomorphic change of coordinate. What happens? W dz. Bar, you agree? No, so I'm sorry. D no. No, sorry. I'm sorry. D bar. So in new coordinates, we obtain operator d tilde. It will be z bar, you see. But of course, we would like to transform to this. Because if you consider the right condition, we can multiply operator by arbitrary function to the left, on the left. So we have the following operator. Sorry, not dw bar. So we have to divide it. D plus epsilon. I'm sorry. Sorry. You see. Therefore, I simply changed coordinate and multiply it, divided by this, to transform to this form. Therefore, this object is of the type B of Z Z bar it has the following tensor weight. That's it. The following transformation law. It has the following transformation rule. This is the transformation rule for this object. Hello? So, okay, well, maybe I'll repeat. I did the following. First of all, I would like, you have a compact Riemann surface. You would like to make variation of the complex structure. First of all, complex structure is such a differential operator, you remember. And variation, infinitesimal variation of the complex structure is defined by this operator. By such operator. And first of all, we study the transformation rule, the tensor type of this object. And the tensor type of this object is this one. Such tensor. vector field with respect to z bar and one form with respect to z. They are called so-called Beltrami, the objects called Beltrami differentials. Beltrami differentials. That's it. Now, so first observation, but of course, some of Beltrami differentials may generate trivial transformation. Now, let's check. Assume that we make a change of coordinates now. Now let's do the following. Assume we have change of infinitesimal change of coordinates. Since we have such infinitesimal change of coordinates, let us check the corresponding change of the complex structure. D You agree? I simply do the following. No, nothing real. Let's write it's dz plus epsilon and using the same rule, we should divide. We have to transform to this way. No, we remove. We have to remove it. We all divide by r, but it's we have to replace it. We have to multiply it to this, and we obtain dz plus you see. But it's high order corrections. You see. It's high order corrections. Therefore, if you have such a change of variables, the corresponding change of complex structure will be the corresponding B, but let me make a remark that it's not invariant. We wrote in the coordinates, you agree. But assume that we have a change of coordinates, holomorphic change. Maybe it's not a good idea, maybe, but okay. Maybe let's not W, but U, for example, will be U. U. Du. What happens? If you make holomorphic change of variables, okay. So it was U, it was in this coordinate system. Now go to the, or maybe, no, let me, Z tilde. Do you mind if I use this? Yes, okay. Use this Z tilde. What happens if we change a coordinate system? The same change of variables. W tilde is okay, let me denote it will be f of z. I think it will be a little better. Use this notation. W is f of z. I agree. It's by definition.
So we consider this holomorphic,
yes? Yes, holomorphic change of variables. You have to find transformation laws of this object. Because we defined in coordinates, but now we have to check the transformation law, the tensor type of the objects. The tensor type of the object. But you see, I simply made a change of coordinates. Is it clear? I think it's something very trivial. But of course, this is the difference between, but W simply write the Taylor series, you see. Therefore, you see that the transformation law is a vector field. Therefore, alpha is tensor of the type alpha is a tensor of the type dz minus 1. Yes. Okay.
Sorry, alpha is a tensor?
Yes, tensor of this type. Okay, dw. You see, we have this form transformation law. Here's some transformation law. Maybe you can write alpha bar, it will be. Let's do this way. In this way, it will be. And this, okay, if you, let's write this way, alpha bar maybe. This is the same, and alpha will be, of course, minus bar. Okay. Therefore, we obtain the following statement, that if, so what we proved? Theorem. Assume that we have a Beltrami differential, B, sorry.
What do I understand by dz bar inverse? Is it just a formal symbol?
No, it's, what do you mean? What does mean this one?
Yes.
It's a transformation law.
This means just for the level transformation.
It's a type of tensor type. What is tensor? Tensor is object with prescribed transformation law. The transformation law will be this transformation coefficient. Simply this form transformation law. Or we can equivalently we can write this B. It's the same. You simply prescribe transformation law. So since we have Beltrami differential, what we proved? That Beltrami differential generates a trivial change of complex generates a trivial.
Which transformation law on dz bar
for dz bar transformation law, for this transformation law, and for the okay, let's check transformation laws. For example, if alpha this dz change z of w w bar I agree. Alpha so it's transformation law for one form. For vector fields, if you have form alpha of z, z bar, dz bar, you go to alpha I agree. Is it clear? Minus 1. But if you have dz minus 1, you will have opposite. Minus 1, okay. I'm sorry, was minus 1. You have beta we have this transformation law for vector fields. Okay? And for H we have the product. Now, what you prove? That beta generates a trivial change of complex structure is equal to generated by a change of infinitesimal change of coordinates, if and only if and only if you prove the following. By the way, it's of course you have to be a little careful. It's one form of course. And okay, but it's not invariant. In invariant form, it will be written as the following. Here's Z bar. Well, it's invariant relation. So, of course, you would like to be a little more careful because you understand that you have to be careful when you differentiate tensor. You should introduce connection. But here, you have this tensor in Z bar. Here you differentiate by Z. You agree. So, it's necessary in sufficient condition. If this Beltrami differential can be represented as D of a vector field of type 0 minus 1 of such vector, if D of, then this change of coordinates is trivial. So we have to calculate the factor space of Beltrami differential. So we have the space, okay. What does it mean? C0 minus 1 means the tensors of such type, non-holomorphic. But it means you see that I wrote. They have the following form, but coefficients are non-holomorphic. This operation D, or maybe D, maps such tensor to Beltrami differentials. And the tangent space to moduli space is you see what I wrote. That the tangent space to the moduli space is a factor space because if it's the transformation rate by change of coordinates, deformation complex structure. You consider all deformation of complex structure, modulus deformations which are trivial because they are generated by change of coordinates. So we have this modulus space. Okay. Such Beltrami differentials factor by the image of this.
Can you please repeat again? Why do we have statement
Yeah.
Why if the differential has this form, then
we considered a generic infinitesimal change of coordinates. And we calculated the formula for change of complex structure. It was exactly this one. That was exactly this one, you remember. We calculated it. Yes. Therefore, it can be removed by a change of coordinates, infinitesimal. Okay? Okay, so we...
Sorry, what is B?
No, B, it was filtering differential. So, generic change, first of all, how we change complex structure? We simply assume that operator D, defined complex structure, is written in the form. It's small variation of the operator dz. You remember? You remember, we did it when we introduced isothermic coordinates. We did it. Complex structure is differentiation operator. So, is such operator.
Complex structure is different.
Of course. What does mean d by dz? You remember, complex structure is a multiplication by I, or which functions are in linear space holomorphic. It's pseudo-complex structure. But in dimension 1, there is no difference between pseudo-complex structures and complex structures. No, of course, we can do the following. As soon as we have multiplication by I, then you, or maybe I, sorry, maybe I, no, but okay, it was possible. Maybe it was better to deform not dz, but dz bar. But okay. I'm sorry, maybe it would be better to do the following. No, d bar operator new. Okay. Z bar, okay, for help, b bar, dz. You see. For example, something like this. Okay, it's complex structure. Because if you have any, what does mean complex structure? Multiplication by I, or equivalently, which you have Cauchy-Riemann equations, you agree. But if you have non-isothermic coordinates, Cauchy-Riemann equations, operator has this form. Sorry, it's okay? Okay. So we prove this following statement. Now, okay, let me omit some analytic moments. Now I would like to formulate something, but I do not want to provide proof analytic details. But what this means? This operator is elliptic. What does it mean, elliptic operator? Elliptic operator means that if you have some differential operator, D, for example, maybe matrix, some operator, in partial derivative, and also some matrix, it's k-dimensional space. It means the following, that if you as soon as you have such operator, what does it mean elliptic? You take higher order term, the high order terms of operator. Then you can introduce symbol. What does mean symbol? You replace you understand that it's like Fourier transformation. And you obtain some operator. It should be, this operator shall be invertible for any non-zero vector sigma. This is true, this operator is elliptic. And for elliptic operator, it means that on higher harmonics, if you have small higher frequencies, it's invertible. And good, it's. And therefore, for elliptic operator, you can extend many properties of finite dimensional operators. And for example, for elliptic operators, at least in these situations, you have Fredholm alternative. What does it mean? So you have linear algebra. We have a system of equations. Ax is y. A is a rectangular matrix. What is necessary and sufficient condition for solvability of this equation? X space V, Y space W. We can introduce a joint operator, you understand. So AX W, a joint operator, A star X from you remember the definition, joint operator. And Fredholm alternative means equation is solvable, equation has solution, Fredholm. Equation solution if and only if Do you know it or not from linear algebra? You recognize it?
Of course.
Okay. So is it okay? You recognize it. Statement. This theorem is also valid. So, okay. Now, and the statement is, I don't want to prove it because it may take too long time, but let me believe. So, first of all, which objects can be integrated over Riemann surface? You have a tensor of the type dz bar. You take the antisymmetric part of the tensor. Okay, so you can do the following. You can understand? It's now a skew symmetric, it's now a one form. So the tensors of the type f bar. Of course, we do this transformation, and we can integrate it. So, okay. So consider the space of such differentials. But of course, we can take the complex conjugation we have. Therefore, we see that this differential, so the dual space it will be C0 to you agree. Because you have to obtain object of the type dz bar. So what we can, if you have differential anti-holomorphic, yeah, this is so this object you see. Sorry, I made a mistake. I'm sorry. I made a small not mistake, but it's better to deform this operator. You understand? Mm-hmm. So I introduce the wrong b. Maybe let's the wrong b, and in this case, b will be. If you introduce this way, okay, let me correct it. If you introduce this way, it will be. I'm sorry. If you make this deformation, now it will be this object. I'm sorry. I transformed the wrong operator. Could you connect? We will deform this operator. It will be dz bar. I'm sorry. We will have this. I'm sorry. We'll try and differential this one. I'm sorry. I made a mistake a little. So it will be space. So we will have C. It will be d bar. You see. That's okay. So we'll try differentials. And the dual space of the space C dual, it will be C to 0. Because here you have objects of the type alpha it has the form structure alpha of z bar z bar. And what's the dual space? Dual space will be objects of f You agree? If you multiply these two objects, you obtain product is alpha of z bar, f of z bar. And this object can be integrated. Remember, I told you. So we have the proper duality. Now, we see that this differential, this Beltrami differential has this representation if and only if it is orthogonal to the kernel, if it's orthogonal to the kernel of the adjoint operator. Remember, I told us what's the solvability condition. The right hand this is orthogonal to the kernel. Is it clear? Critical.
Sorry. Why C minus 1 in star?
What is dual? You have to multiply the product.
Why dual C 2, 0?
Because what? We can multiply this by this and obtain object of this type. We can integrate such tensors. You understand, we take. Which tensor can be integrated? Of course, you have to make
Scalar product is integral.
yes.
Okay.
The,
I see.
well, the scalar product is. Okay, let me write the scalar product as integral over gamma, and this is this scalar product. We write use the scalar product. You understand? We can integrate this object. I prefer you see. What's the natural measure? What's the natural measure? Not measure, but what we can integrate. No, which objects can be integrated over gamma? Sorry. Two forms. Yes, one forms. One forms, but in different. Two forms, but you see.
The definition scalar product.
Yes, we define scalar product in this way. I have is not essential, but. So this is okay. Because what we can integrate? We can integrate forms of the form of a gamma, for beta, or you agree. What is the natural object of integration? You agree? It's okay. What we can integrate over gamma? Only forms of this type. You agree? Is it okay? Sorry. But of course, if we have such form, we have such form. If we have such form, we can also, but soon we have form beta this is bar. Okay, I prefer to multiply to I divided by 2. You agree? Well, you prefer. It's a constant multiplier. Of course, I can construct by it. This is bar. Of course, it's anti-symmetrization. It's correct operation. So, such forms also can be integrated. You agree? So, you can integrate such forms. Then, if you have form alpha bar n, then dual form will be f You agree? Dual spaces. Because the product shall go this way. So the dual space as is in this. Okay, sorry, if you multiply, you obtain the object dz, dz bar. Okay, you multiply, you obtain the product is.
Is it bar or prime one?
Yes, of course, yes. I make no complex conjugation.
No.
Yes. So naive dual. But okay, so so we have this dual space. The form. I write, make no complex conjugation. Therefore, it means the following. Finally, what you found? Finally. This form can be represented in this way. So we if and only if the differentials. Omega is the type. Omega. You remember. For all omega. For all such omegas. But we proved that dimension of the space is, but we, at the previous lecture, using the Riemann-Roch theorem, we calculated the dimension of the space. You remember? It was 0. Complex. You remember? And we know that factors, the dimension of the factor space is exactly the dimension of the space. Okay? Is it clear? First of all, we proved that deformations of complex structure are defined by such differentials, okay, called Beltrami differentials. Beltrami differentials. Then Beltrami differential is trivial, usually trivial, if and only if can be represented in this form. It's d-bar operator. The adjoint operator also d-bar, we don't put complex conjugation. Therefore, this form generates trivial transformation of complex structure if and only if it's orthogonal to the kernel of the adjoint operator by Fredholm alternative. But we calculate the dimension of the kernel of this operator at the previous lecture, adjoint d-bar. D-bar acting of two forms. Remember? Holomorphic two forms we found. Therefore, the dim of moduli space is this one. Moreover, it's more or less explicit. We simply we have this basis of the forms. And we check if the product is zero, it's trivial deformation. If the product is not zero, it's non-trivial deformation. Okay? So it is clear. So we calculated the dimension of the moduli space. Yeah, I remember if you have string theory, you heard about this dimension. You recognize? I think it was mentioned. But okay. Nevertheless, I am preparing. Okay, but I hope I explained. Modulus is Fredholm alternative, but okay, you can believe. In fact, it's possible to prove it explicitly that Fredholm alternative is correct, but let me omit it. Because I very short in time, so let me start a new topic. I will start. Let me spend the remaining 10 minutes for a new topic, or 5 minutes. The new topic will be the following. How to, because I hope, at least in the conformal field theory, the most popular object is Virasoro algebra, or Virasoro algebra with zero central charge. Let's start from Virasoro algebra with zero central charge, with algebra. It's an algebra generated by vector fields on the circle. We have unit circle in the complex plane. We have vector fields. Okay, it is LK. This is algebra vector fields. Let me describe the action of this algebra on the moduli space of Riemann surfaces. But it will be slightly modified. Consider such extended moduli space to have really right commutators. Assume we have Riemann surface. With a marked point, P. First of all, we have Riemann surface gamma. Second, marked point P, or P0. The third, local parameter. So we have gamma, we have marked point on gamma, and we have local coordinate system near this point. We also assume that you have local coordinate near this point. So, by the way, why important? Krichyver worked exactly with such construction in his famous KP work. Riemann surface, marked point, local coordinates plus divisor. But okay. So consider such space. Riemann surface, marked point local coordinate. Then we can represent the Riemann surface in the following form. We have Riemann surface with a hole. We have some Riemann surface with a hole. Okay, so with a hole. We have a patch. And let me do in opposite direction, glue the surface to the patch. Not the patch to the surface to the patch, but not a big difference. You see, we have some gluing law. You see? Can we do it? We have, moreover, on this patch, we have marked point P0. You have a local coordinate Z. Okay.
Sorry, boundary is geodesic?
No.
Okay.
Simply a hole. You see. So we remove
Through hole?
Neighborhood, some small area, you see. You glue this area to this one. And you do it. I think maybe Kodaira Spencer, I think, will its construction also. Then you can do the following. Consider a vector field here. So that you have a vector field. And you can shift any point along the vector field. If you have vector field here, you need to have vector field near this circle. I think we have a unit circle here. You have here a unit circle. You have a vector field in the neighborhood of the unit circle. But of course, it's not defined here. It's defined somewhere here, not here. It's not necessarily holomorphic inside, not necessarily holomorphic outside. It's also holomorphic near this contour. You see. Then you can move a point x. You understand this notation. I simply integrate differential equation for the period time epsilon. Shift, we have vector field, therefore we can shift a point along the vector field. Understand it? Is it clear? So we, instead of gluing to this point, we glue a new point. If originally y was attached to x, deformed, y is glued to exponent we glue to a different point. Okay, understand?